Hello and welcome to this video where we attempt question 2 from the June 2019 Edexcel Decision Maths paper. In this question, we've got figure 1 representing a network of corridors in a building. The number on each arc represents the length in meters of a corresponding corridor. And we're asked to use Dijkstra's algorithm to find the shortest path from A to D. We want to state the path and its length. So we're told which vertex to start from. We're starting from vertex A. So I'm going to label A first. So I'm going to put number 1 in this box. And the distance from A to itself is 0. And now I'm going to update all of the working values of the vertices connected to A. So I'm going to get working values of 38 for B, 75 for C, and 42 for F. Of these working values, or of all the working values of vertices we've not visited, B has the smallest one. So I'm going to visit B next. So I'm visiting B second, and I'm going to finalise value 38. So now I'm going to update all of the working values of vertices attached to B. So I'm going to get 53 for E, because that's 38 plus 15. I'm going to get the value 80 for D. So now I'm going to look at all the working values of vertices I've not visited, and of these, F has the smallest working value. So I'm going to visit F next. I'm visiting F third with a final value of 42. And I'm going to update all of the working values of vertices connected to F. So I'm going to get 62 for C, I'm going to get 54 for G, and I'm going to get 81 for H. So I'm going to look at all of the working values of vertices I've not visited. And now I'm going to get 53 versus 54 versus the rest. 53 is the smallest. So I'm going to visit E next. So I'm visiting E fourth. And it has a final value of 53. So I'm going to update all the working values of vertices connected to E. I'm going to get 63 for G, which isn't as good as 54, so I'm not going to write it down. I'm going to get 70 for J. So I'm going to write that one down. So I'm going to repeat this process again. Smallest working value on a vertex I've not yet visited is 54. So I'm going to visit G next. I'm visiting G fifth. It has a final value of 54. So I'm now going to update the working values of all the vertices connected to G. So 54 plus 7 gives me 61, which is an improvement for C. 54 plus 23 gives me 77, which is an improvement for H. And 54 plus 14 is 68, which is an improvement for J. So now I'm going to look at all the working values of vertices I've not yet visited. I've got 61, 80, 68, and 77, of which 61 is the best. So I'm going to visit C next. C comes 6th, and it has a final value of 61. All of the edges connected to C have already travelled down and considered, and all the vertices connected to C have a final value already, so we don't need to do anything. So I'm going to do this process again. I'm going to visit the next vertex with the smallest working value, which is 68 or J in this case. I'm visiting J next. J comes 7th on my list with final value 68. I'm going to update the working values of those around it. I'm going to get 78 for D. I'm going to get 74 for H. I'm now going to visit the next vertex with the smallest working value, which is going to be H, 74. So H is being labelled 8th and has a final value of 74. All of the vertices connected to H have a final value. And last but not least, I'm going to visit D. So D comes 9th with a distance of 78. So The length of the shortest path from A to D is going to have a length of 78. That's what Dijkstra's algorithm tells us. And to find the shortest path from A to D, we can backtrack by taking the final value at D, subtracting the weight of each edge connecting to D, and if that gives us a final value of the previous vertex, or the vertex at the other end of that edge, that vertex will have come before D. So I take D, 78, and subtract 10, I get 68. So this edge lies on the path. 68 subtract 14 gives me 54. 54 subtract 12 gives me 42. And finally, 42 subtract 42 gives me 0. So it looks like I've gone from A to F to G to J to D. And if we look at the marks of this question, we're going to get a method mark when a larger value has been replaced by a smaller value in at least two of the working boxes. That's either C, D, E, G, or J. And we've done that. We've got 3 boxes where we've done that, so we're going to get a method mark. And accuracy marks come from having values all correct in A, B, F, and E. So our first accuracy mark for A, B, F, and E. Our second accuracy mark for values being all correct in G, C, and J. And our next accuracy mark for having all correct values in H and D. Last but not least, we get an accuracy mark for giving the correct shortest path and the correct length. So next up, we're told that on a particular day, Nasir needs to check the paint work along each corridor. And Nasir must find a route of minimum length. And the route must traverse each corridor at least once, starting at B and finishing at G. So this appears to be a route inspection problem. So for this, I'm going to number all of my vertices with the order of each vertex. So I'm going to get A has degree 3, B has degree 3, D has degree 2, J has degree 4, H has degree 3, F has degree 4, C has degree 3, E has degree 3, and G has degree 5. So we've got 6 vertices of odd degree, which is a lot of vertices, a lot of combinations of routes we can take between 6 vertices of odd degree. So we're actually told that the route starts at B and finishes at G. So really, B and G can have an odd degree, and that's absolutely fine. So we don't need to consider B or G. We don't need to consider vertices with an even degree, D, J, or F. So the vertices that we really need to consider are the following vertices. We need to consider A, C, E, and H. And all the combinations, all the pairings of A, C, E, and H, and all the minimum lengths between those pairings. So the first pairing we're going to get is AC and EH. And the shortest path from A to C we can actually find using Dijkstra's algorithm. So A to C has minimum length 61. The minimum length from E to H is from this vertex up here to this vertex down here. And if we look at the graph, we can either travel 10 plus 23, which is a distance of 33, or we could go a bit shorter and can have 17 plus 6. So E to H has a length of 23 via J. The next pairing we need to consider is AE and CH. And again, AE, we know the minimum distance from A to E from Dijkstra's algorithm. It's going to be 53. And CH can consider the shortest distance from C to H. And the shortest distance from C to H, well, we could do 20 and 39. That's going to give us 59. We can go shorter. We can do 7 and 23. That's going to give us a distance of 30. But we've already seen that going G to J to H is quicker than G to H directly when we perform the Edexcel algorithm. So going C to G to J to H actually gives us a total length of 27. And finally, we need to consider the length of a route AH and CE. And A to H has a distance of 74. So I already think this isn't going to be a good solution because we've not got much room for error before the previous solution beats it. And then CE, we can really clearly see that C to E has distance of 17 in total. So we can add these numbers up. The first pairing or set of pairings has a weight of 84. The second set of pairings has a weight of 80. And the final set of pairings has a weight of 91. So we're going to choose a second set of pairings. But when we're asked to state the arcs that need to be traversed twice, the answer is not AE and CH. These are the paths that we need to traverse twice. So a path starting at A and ending at E, and a path starting at C and ending at H. And to get from A to E in the minimum distance possible, we need to go from A to B to E. So actually this path is A to B to E, and the path from C to H actually goes from C to G to J to H. I'm going to write that down. C to G to J to H. Which gives us arcs AB, BE, CG, GJ, and JH. And we want to find the length of Nasir's route. So the length is going to be the weight of our graph that we currently have, 370, plus the length of the arcs that we're adding, which is going to be 80. Which is going to give us a route of 450 metres. Finally, on a different day, all the corridors that start or finish at B are closed for redecorating. And Nasir needs to check all the remaining corridors and may now start at any vertex and finish at vertex. And a route is required that excludes all of these corridors that start or finish at B. So we want to determine the possible route of possible starting and finishing points so that the length of Nasir's route is minimised. We need to give reasons for our answer. So part D, if we remove B, we now need to list the nodes that are odd. And removing B will decrease the order of all of the vertices connected to B. So we're going to get new degrees. A is now going to have a degree of 2. E will have a degree of 2. And D will have a degree of 1. So the vertices with an odd degree are going to be C, D, G, and H, because G is now being considered. So if we remove B, then C, D, G, and H are odd. So if C, D, G, and H are odd, and we can start and end at any vertex, we're going to want to start and end two of these vertices, as that prevents us or stops us from having to traverse multiple pairings twice. As if the vertex is odd, then the first time we leave it, or the last time we enter it, we only have to leave or enter it, which means that we're only using one of the edges going in or out of it. So the possible pairings we have are CD, CG, CH, DG, DH, or GH. We want to find the shortest route between all of these vertices. So we can look at our graph, and if we look at our graph, we're going to get CG is 54, so we can add that in. CG is 54. I'm going to try and find CD. CD appears to have a length of 31. So if we go to our graph, if we do C to G to J to D, that has a length of 31, but appears to be the shortest for CD. C to H, we actually found before, was 27. And then we've got DG. DG has a distance of 24. So DG is better and is currently the best. DH has a distance of 16, 10 plus 6. So DH has a distance of 16. And finally, GH has a distance of what is that? 23, but we could actually get 20. So GH has a distance of 20. Looking above, I've actually got CG incorrect. I accidentally did something different. I just looked at this 54 here, but CG isn't 54, it's actually 7. My apologies for that. So CG has a distance of 7. So CG is the best option for an edge or for a route to repeat again. So we're going to start /end at D/H. I'm going to traverse CG twice. So doing this, we're going to have a length of 370, but then you've got to take away all of the weights of edges connected to B. So 38, 42, and 15. So subtract 38, subtract 42, and subtract 15. And then we've got to add in the path connecting C and G, which has length 7. So the distance of this new route, or the length of this new route, is going to be 282 metres. So looking at the marks for this second part of the question, I'm going to get a method mark for trying to pair up vertices that have an odd degree. I'm going to get an accuracy mark for doing one of these correct, another accuracy mark for doing the second one correct, and the third one correct, and choosing the best solution, and one final accuracy mark for giving the arcs. We're going to get an independent accuracy mark for the length, which is also a follow-through, depending upon your solutions before. And then for D, part 1 and 2, we're going to get a method mark for saying which vertices are odd. We're going to get an accuracy mark for saying that we need to traverse CG twice. And finally, an independent accuracy mark for giving 282 metres. So thanks for watching, and until next time, thank you.